And we are going to then start with our note. And so at this point, please put those marks aside. So Brett, you need a piece of paper. You need to write down refraction. And the date wouldn't hurt. Oh, Tyson's getting ready to work hard. It's what? Here, put some tape on those spots that you feel are affecting you. Okay, sound like a plan? There's 4 there. Okay, refraction. Tyson was looking at the pictures yesterday. Didn't want to read the words, but that's okay. It's a start. He was looking at the pictures. And from that picture, he was able to determine what refraction is. What is refraction? Did anybody remember from yesterday's reading? What is refraction? Yep. It's how light bends when light enters a new transparent substance. All right? The reason, did anybody get from the reading why the light bends? Why does the light bend? No, it doesn't reflect. We just learned the word refraction. We're not dealing with reflection yet. Correct. The transparent medium, the thing that we're looking at, whether it's water or glass or a diamond or oil, it doesn't matter. That transparent medium, the speed of light changes. Remember we talked about how light goes fast. And we put a great big number up there, 3.00 times 10 to the 6th meters per second. It goes crazy fast. Or sorry, times 10 to the 8th meters per second. It goes really, really fast. But when it enters a transparent material, it actually slows down a little bit. Now, the fastest the light can go is in nothing. Where can light encounter no substances whatsoever? Where do you think light travels the fastest? Out in space. So when the light leaves the sun, because it's hot and that light takes off from the sun, it's going as fast as it possibly can. It's going its top speed. And then as the light that we see here on Earth enters the air, it slows down just a little bit because the air is pretty thin. So the speed of light in air is almost as fast as the speed of light in space. It's just a tiny bit slower. But then when the light enters something like water or glass or diamond or anything that's transparent, it slows down more. And it's this slowing down that causes the light to bend. Let's take a look at some bending light here. This is some equipment I'm going to get you guys to look at here in a moment. And here we've got some water. Now, that light already is bending when it hits that water. That's the light that's kind of coming in from the room. The reason I know that it's bending is because I can see the edge of the water. When the light bends, even though it's transparent and the light can go through, it bends it enough for our eyes to detect, and then we can locate where the water is. If the light didn't bend when it went into the water, we wouldn't be able to see the water. The only reason we can see water and see glass and see a transparent material is because the light is bending. That's why it kind of looks a little goofy when you look into this aquarium here, or whatever you want to call it. Okay, so now let's take a look at this and see if we can actually see it bend. I shut some lights off here, okay? And I've got a laser beam. It would be nice if we could do our experiments with a laser beam, because what's the good property about a laser beam that isn't so good about our ray boxes? Our ray boxes aren't that great. What's not so great about my ray box here? Yep, what do you got, Cade? Yeah, see how that beam gets so wide over there? It spreads out. So the ray boxes are LEDs, they spread out. Lasers are great, they don't spread out. So here I've got a laser and there you can see it hit the wall. Why can't I see the laser go through the air like on the movies, or like on, there was one they had on, I believe it was on Big Bang Theory. They had to crawl through the room to try to play chess or something, some kind of goofy thing. Why can't I see the beam as it travels through the air, but I can see the beam as it hits the wall? Why is that? Yep, Cade? Nope, it's not speed. Nope, good guess, but it's not. Why can I see the wall itself? Why can I see that wall over there? Light, what's happening to the light? It's being absorbed. If it was being absorbed, there'd be no light left, and I wouldn't be able to see the wall. It's being reflected by the wall. So it hits the wall, it spreads out, it's reflected, it enters our eyes, we see the wall. I turn on the laser, it hits the wall, it's being reflected, it comes into our eyes, we see the wall. I want to see the beam in the air. What do I have to do if I want to see this beam? Yep. Go ahead, Cade. Sorry, not Cade. Lucas? That was my mistake. I got to put something in the way. I can put my finger in the way, right? There, I don't know if you can see, well, I can put my finger in the way, but if I had this, and I used to use chalk dust is really kind of a dirty, messy stuff. This is special, special dust that's used in special effects. There you can see I've put some stuff in the way, and there I can see the beam. Like in the movies, exactly. It's always there. You know how it's always there? That's really kind of dumb, because if they, you know how the bad guys walk in and they say, "Whoa, look out! There's a laser trip thing. Watch it." They crawl over, and they can see it perfectly. The people who want to make their stuff secure, they're not going to have a nice dusty air so that they can see the beam. They're going to have it nice and clean. Now, the reason I'm saying this is, if I take this laser beam and I shine it into the water, there you can see a little bit of my dust is still left. If I didn't put that dust in the air, we wouldn't be able to see it. Now, I want to show you how the beam bends. But can we see the beam in the water? Don't be distracted by the beam on the ceiling. All right? Abby is totally distracted. She's like, "Whoa, look at that. There's two of them. Wow." Don't be distracted by the beam on the ceiling. Why is there a beam on the ceiling? It's reflecting off of the surface of the water. We did reflection. Just relax. We don't need reflection anymore. We're worried about the beam in the water. Can you see the beam in the water? No. Why can't we see the beam in the water? For the same reason we can't see the beam in the air. So what do I have to do with the water? I got to put particles in there. Now, I used to put glue in it because glue worked perfectly, white glue. The last time I used this white glue was to do this experiment, to do this demonstration. That was probably about 5 years ago. The glue is separated a little bit. It's not going to glue anything. But I'm hoping that that liquid on the top has enough little particles in it that it will, it won't come out. So obviously this is working really well. I'm going to push this, there's going to be all kinds of it. It's going to just make a mess. What if I get, all right. There we go. Oh, goodness gracious. This is disgusting. That's old glue. Ooh. All right. So you can see there's a little bit of dust in there. That's exciting. I'm going to stir it around. So what I've done is I've now put some glue particles in there. Glue is made up of a polymer called polyvinyl alcohol, and it's suspended in water, and you can see that that's separated out. So now I've put some particles in the water, and I can see the beam. Awesome. Now, what we've got to do is we've got to take a look at what happens to the beam between the air and the water. So now I need to add some dust there. All right, let's take a look. Now, as I bend like this on an angle, can you see that the ray bends? Goes in, and how would you describe which way it bends? Down. It bends down. Now, you'll notice you can see there's a little bit of a reflection up there. There it is, there's a reflection. And you can see that there's another reflection off of the bottom of the glass. Do you see that other reflection there? That's what makes the second beam, right? The second beam is off the bottom of the aquarium. The first beam is off of the surface of the water. If I hold the beam really still, notice what happens to that first beam. What's it doing? It's oscillating. Why is that first beam moving a little bit? Because the water's moving. The surface of the water's got a little wave on it. So as the wave comes by, it wiggles the first one. That's not what we're studying here. That's just cool to think about. Okay, so we take a beam, which we can't see anymore, that's going in to the water, and we can see that it bends down. When light enters a transparent medium, when I say medium, I don't mean the size between large and small. I mean a substance, some kind of substance, a medium. It slows down and it can bend. And that's what we want to write about. So, refraction. And I do want you to write this. All right? And let me describe to you what you're seeing. This picture here represents waves, like waves on the ocean, where each of these lines is the wave coming in. All right? So all you've got to do is make a series of lines, and you don't have to make as many lines as I have on my drawing. You might just put 1, 2, 3 lines, and you might just put 1, 2, 3, 4 lines on the bottom. But what's the important part about the picture? What's got to be different about the lines on the top compared to the lines on the bottom? Yep. They have to be more spread out. That is correct. So what we're saying is, if waves come in to a region where they move slower, then they're going to bunch up, and they're going to pile up on top of each other. So the waves are piling up on top of each other. Think of it like cars on a freeway. If you've got cars going 120 kilometers an hour, everybody's spread out nicely. And when you end up in maybe entering Toronto where the traffic is different, what happens when the traffic slows down? Yeah, all the cars bunch up. Same thing here. The waves of light are coming in, they're going top speed, they enter the water and they all get closer together. They slow down. We use the term optical density. Density means something that has a lot of mass in it, right? It's very heavy, like lead is very dense. When we say optical density, we mean that it's slow for the light. The light goes slowly. So air, we would say, has a low optical density. It travels fast. Water, we would say, has a high optical density. It slows the light rays down. All right? Now, on my next slide is a picture. And ideally, I guess we could use a protractor to draw this next one. So I will hand out protractors again. Again, if anybody has found the protractors that you borrowed from the last time, that would be great. There's 4 protractors. You can take one, send it back. There's a couple of protractors there. If you already have a protractor, actually, Pat's not going to write any. Oh, he is writing stuff down. Nice. Give Pat a protractor. Exciting. 2 protractors there. Here, we'll deliver one back to Max. And 1, 2, 3, 4. Oh, and I'm going to be close. Oh, Mitchell has his own. Oh, nice. I'll take one back. Beautiful. Mitchell, you got your own? So 1, 2, 3 right there. All right. In my next picture, I want to draw what we saw here in the little aquarium. I want to draw the ray coming in. I want to draw how it bends, all that type of stuff. I'm going to put it up on the screen, but watch me. I'm going to draw it for you. I want you to follow my writing, all right? So that's up on the screen for the people who are watching the video. I want you to follow me. So down here, you're going to just draw a line. Like that. Okay? And that line is not a mirror. So we don't put the little marks that we've been putting for the mirror. That line is the surface. It's the surface of the material that's coming, that we're firing the light in. Surface, in this case, we could put H2O, just as an example, e.g., like the surface of the water. And what I want you to do now with your protractor, I got to grab my big protractor here, is I want you to draw a normal. Now, this is why we draw normals. So, on the 90, with your zeros, put a dashed line, but now the normal goes all the way through, because our light is now not going to just bounce off, but it's going to go right in through. So again, I'm going to put a little label here. That's the normal. And now I'm going to draw an incident ray, just like we saw for reflection. And I'm just going to take it and make it whatever angle. Again, you can do the same thing. It doesn't matter what the angle is. Just draw a ray that goes in there. Okay? And we will again label that the incident ray. The incident ray. Now, oh look, I got something wet on the chalkboard from my hand being wet. So now, let's first deal with the reflected ray, and then we will deal with the one that goes through. We saw that a little bit of light reflected off of the surface. That's why we can see the surface of the water, because a little bit of it comes into our eyes. So I'm going to measure the angle of incidence again. For me, it's 63. I'm going to flip over to this side, and again, I'm going to mark my 63, just like I've been doing in the past. Whatever yours is, that's fine. And we're going to then draw on the reflected ray, because light does reflect off of surfaces that are transparent. And this is just like we finished on our test. The reflected ray, or the incident ray, which is just fun. We've already seen angle I, and the little I is important because the reflected is called angle little r. Now, some people on the test, when they were labeling that, put a capital R, and I wasn't picky about that. But now I'm going to be picky, because our refracted ray needs an angle as well, and we use the capital R to represent that. Now, how do we draw this bent ray? Let me show you. Start by putting your straight edge, whether it's the ruler or the protractor, it doesn't matter. You probably just have a protractor. Put it right on the incident ray. So you've got a reference point, but don't draw a line. Don't do it. Put it on the ray, and then which way did that ray bend compared to that? Down. So now I'm going to turn it down. And I'm going to turn it just down a little bit. And I don't care how much you turn it down. Okay? Just turn it down a little bit. Now that it's down a little bit, I'm going to draw that on there, and I'm going to put my arrow on there. Okay? We're going to do an experiment in a bit where we're going to see how far down it moves. All right? This angle in here is angle capital R, the angle of refraction. I'm going to put a little definition off to the side. Angle capital R, the angle of refraction. The angle of refraction. The last thing I want to write in here is that this is the refracted ray. The refracted ray. And you can now then write on here what refraction is. All right? What refraction is. You can write that definition. Okay? Again, I like to draw it on the board because sometimes it's easier and better for you guys to see how I'm drawing this. Before we do our experiment, I want to talk a little bit about what happens if the light were to start in the water and go out into the air, okay? And we're going to take a look at that in a moment. Now, before we do that, and Tyson's already ahead on the next slide, and that's great. You don't have to write that down. That's just this thing on the next slide, and I'll just wait for everyone to be finished. Helps us kind of figure out which way the ray is going to bend. You guys are saying that it's going to bend down, but what if I were starting with the ray coming in the water out into the air? What's going to happen to it? So we need an official way to write down what happens to those bending rays. So let's first come up with this little analogy that's on my next slide. Let's first talk about how can we remember which way it's going to bend. All right, and that's what I want to talk about here in a moment. So notice you guys said that it bent down, and this next, oops, you guys are, it's frozen, so you're not able to see what I'm doing here. Back up, back up. So let me unfreeze this. Freeze. So this is the analogy that someone has come up with, and I like it. When the light comes in, it bends down. Think of it like driving a vehicle, all right? If you had a vehicle driving along on regular pavement and then it ends up getting stuck in the mud or ends up in the snow, you may have noticed this riding in a car, or if you're starting to get your license and driving, you may have noticed that as you travel along on the pavement, everything's good, but if the first wheel gets caught in the mud, then it's going to slow down, and the other wheel is still on the pavement, it's going to go fast. So what that does is it twists the car around. It twists it so it gets stuck in the mud more, and it bends down. If you ever get stuck in the snow, you got drifts on one side of the snow, the snow pulls you into the snow more because the right side of the car slows down, the left side of the car keeps going, and it turns you into the snow. So when the light ray is going fast and then enters that slow medium, the slow water, it turns the ray. So what is going to happen if we do the reverse? What if I have the light coming from the slow, think of the car wheels, and then goes into the fast of the air. So the wheels are spinning, and then it catches the dry pavement. What's that going to do to the twist? How is the car's direction of travel going to change when it gets to that dry pavement? It should twist away, right? It should turn away like that and take off and go fast. So notice this one bends down, but this one's going to bend away. Let's test it out. So again, I'm going to need a little bit of dust in here. I'm going to need to turn off some lights. I'm going to need my laser. And this time, I'm going to put the laser right up against the glass. All right? And you can see there's reflection. Don't worry. Actually, you know what I got to do? I've got to get closer to the edge. I can do it from this end. I've got to get into the. I've got to get into the sink. Oh, and look at now. I've got a really bad, wiggly, wobbly water. Terrible. Can you see the ray? Yeah. See how it comes in, and then see how it takes off away. See, even though the water's moving, you see it dip up and down. Yeah, it's going crazy on the wall because it's moving. But there, it takes off away. All right? So we need to write down a couple of rules of refraction. I'm going to come back, and actually, this is not a bad little animation. So in this animation, you can see that the light rays come in, they bend in, down, and then they bend away, and then they travel away after that happens. So that's not a bad little demonstration there. We're going to talk about that in a moment. First, we're going to write down the two laws of reflection. First, we're going to write down the two laws of reflection. And then we will go back and we will take a look at what happens when it hits a rectangular prism, because that's what our experiment is on. So it has everything to do with whether you're going from fast to slow or whether you're going from slow to fast. And we think of the bend with respect to the normal. When going from fast to slow, like from air into water, we say that the ray bends towards the normal. So now I don't want to use the term down, because what if I have a piece of glass that's sitting upright like this? Up and down doesn't have meaning. So we reference everything to the normal. Going from fast to slow bends towards the normal, puts you in the ditch. From slow to fast bends you away from the normal, gets you away from the ditch. The ditch is slow, the road is fast. Does that make sense? I do want you to sketch these three pictures. Just put a line and then perpendicular to it, put a dashed line. And it doesn't have to be with a protractor unless you'd like to, as long as you draw them quick and make them kind of a good sketch. Put it away. And then we'll work through these three examples together. Air into water. Here the light's coming from air going into glass. And here the light is coming up from the water going into the air. And again, they just have to be sketches. If I were drawing these in my notes, I'd go like this. I'd draw it fairly fast. I'd go like this, like that. And then I would just draw a ray coming in like this, and then I'd write air, and then I'd write water. Because I'm really just worried about the bending. Where is it going to bend? Well, let's work on the first one together here. Well, air versus water. What is fast and what is slow when it comes to light? Air versus water. What is fast and what is slow? Tyson, what do you think? Air's fast. Fast, slow. So according to the rules, this light is going from fast to slow. How should it bend? Just tell me the rule. Fast to slow, it should bend towards the normal. So how do we do this? Again, that's straight. Right there is straight. So towards the normal is that way, making it closer to the normal. They're straight. that's closer to the normal. So there is straight. Oops, that was terrible. That was the absolute worst drawing. Did I not orient the board? Is my pen not where I think it is? All right, that's a little better. Oh, I can't even put the arrowhead on it. That's horrendous. That was supposed to be closer to the normal. So when going from fast to slow, bends towards the normal. Air versus glass. What is fast and what is slow? Air versus glass. Josh? Fast, slow. According to the rules, how should it bend? Towards the normal. Notice here's the normal. The normal is now 90 degrees. That's where it was going originally. Here, I'll use a shadow. I've now got to go closer to the normal. That way is closer to the normal. So there is straight. There. I got to go up a little bit on this one. I got to get it closer to the normal. And I don't, look at my pen is so far off, it's terrible. Something has bumped my cart, but that's okay. I can adapt. That looks like it bent up. Oh, actually, I know there's only one person that could have bumped my cart. No, maybe two. So, closer to the normal. So notice how it bent up a little bit there. That's okay, closer to the normal. Again, we've already done water and air. Slow to fast. So how should this one bend? In this case, look at, where's the ray starting from? It's starting from the slow medium. I know I put water on this side, but this is a normal. This whole area down here is water. This whole area down from this line is water. So it's going from slow to fast. How's it going to bend? What does it say in my rule? Yep. Away from the normal. So there's the normal. That straight, it's got to get away from the normal. It's got to get away. Oops. Oh, Tyson, goodness, look at what you've done to me. Away from the normal. Away from the normal. One little kick. So there's straight. I got to bend it away from the normal. Okay, so we're going to be doing a lab right now. And I have paper supplied for you over there. If you want to do it on paper, though, right, you're going to have to write the purpose and the observations and answer the questions like we've been doing in the past. I'm going to stop my recorder right here, right now for a minute. So we'll stop the recorder. You can go to Google Classroom and you can open up the lab